Hello, hi everyone. Thanks for um, being here today. So my name is Sean. I'm one of the co-founders of NinjaVan. So I'm the second Sean for today. So I really enjoyed Sean Ma's presentation today. So yeah, I'm very pleased to be able to host together with the TiDB folks, the TiDB user group. Really hoping that we have a lot of future sessions and get to know one another, share our problems. Yeah, I think lots of interesting things we can talk about. So maybe I can take a bit of time just to tell you guys who we are. We are a company that started off in Singapore about 6 years ago. And currently we are present in 6 countries in Southeast Asia. We deliver about upwards of 1.5 million parcels every single day. And yeah, we rely on huge amounts of technology to keep us running, optimize everything all the way from the customer experience to the operations and the after sales and everything, right? So yep, Singapore, and after about 10, 11 months operating in Singapore, we went into Malaysia, and right now 6 countries, 30 over 1,000 employees. So it's been very, very quick growth for us. What that means when you translate it to our tech is we've had to scale very, very quickly. So everything about our tech has always been about reliability, scalability. So that's what my personal interest as well. Distributed systems and also database engineering. So these are some of our customers. Hopefully you guys are buying more stuff now and staying at home, keeping safe, and yeah, we'll deliver all the goods to you, make you happy. All right, so here's what we're going to talk about today. Firstly, we'll explore a little bit about how we are doing OLTP in NinjaVan. Then, what's next for us, right? What's our next generation database, both on the OLTP as well as the analytics side of things, right? Then I will hand it over to one of my senior platform engineers, Meng Nan. I'm really excited for his session as well. We'll talk about how we're starting to operate TiDB on Kubernetes and some of the pitfalls. All right. Okay, so yeah, we deliver millions of parcels every single day, and I just wanted to just give you an idea of some numbers. We do in the scale of billion API requests. We ingest a huge amount of data every day, and we're built on a microservices architecture, right? So 100% of our system, our applications are deployed on top of Kubernetes, with the exception of our OLTP databases, which are still on VMs, right? But anyway, moving forth with times, we're even in the process of shifting those MySQL servers into Cube with the maturity of like the PVs, the PVCs. So yeah, and some of our databases are already in Cube. So yeah, no prizes for guessing. Most of our databases are on MySQL. Yeah, but before I talk a little bit about that, I just wanted to first of all give a shout out to all the NinjaVan engineers who are in this call, right? Thanks for supporting us, right? Yeah, we are an engineering company, so we're always hiring people all the time: database engineers, system architects, software engineers, right? So yeah, this could be you. Okay, so on to NinjaVan's apps. So I said we have about 100 microservices in our system. We mainly rely on MySQL for OLTP storage, and generally our applications exhibit very high read-to-write ratios, right? That's usually the case for most applications. Even more numbers. Now I'm just focusing on our databases. Now we maintain about 70 VMs, and that's excluding the MySQL instances that we've already pushed to Cube. We have about 100 plus schemas, and some of our tables, especially those that store huge amounts of audit trails, events, they are to the size of terabytes. Okay, so how do we run MySQL within the company? We actually use something known as Galera. I'm not sure if some of you guys have heard it, but if you have not, it's basically just MySQL binary together with a Galera plugin, right? You can Google what that is. But to just cut the long story short, it's kind of like a HA solution for MySQL, and it allows basically all the nodes in the cluster are all masters. So you can write to any of the nodes, and you can also read from all the nodes, right? So it's quite easily read scalable. So notice I say it's only read scalable, not really write scalable, because in Galera replication, basically all nodes are full replicas of one another. So a write on one node will result on a write on all nodes, right? So it doesn't have any sense to actually even load balance the writes. In fact, for us, as I'll show you later, we actually keep the writes on a single node, and we actually do read-write splitting across the other nodes. So here's a very simple diagram to explain how that works. So on the left side, you have the microservice, right? And on the right side, you have the Galera cluster. So in between, we're using something known as ProxySQL. It's basically, again, another open source project that it's an SQL aware layer, and you can do a lot of cool stuff on it. You can define query rules. You can use it to ensure that you can use it to maintain high availability as well. So inside this diagram, you'll notice that I select the node as a virtual master. Now this is important because generally how it is, right, is when you have replication sometimes, and if replication is asynchronous, sometimes you will have delays going to the other nodes, right? So if you're doing anything that requires strict consistency, like account transactions, and you make a deduction, the writes will go to the virtual master. And if you want to have a consistent read, you should read from this virtual master as well, because you risk getting stale data if you read it from the other nodes. So this wrong computer. Yeah. So this is just an example of how we can achieve something like that using ProxySQL. So all we do, if you look at this rule here, we're inserting two rules. And the first rule over there is if we detect, sorry for all the slashes, that's just to escape the slashes and the asterisks. If we detect a comment in the query, ninja_critical read, we will route it to destination host group 10, right? If it doesn't match, then it will go to host group 20. So what we do is the host group 10 is basically that single master server, and the host group 20 is the other two servers, right? Then on line 4, you can see we set the default host group to 10, which means that everything else, like your writes, updates, deletes, they just go to the host group number 10. Okay, so I did say that this solution is unfortunately not very write scalable, because every write is basically broadcasted. So actually, one of the use cases of ProxySQL is you can do some kind of sharding. There are a few kinds of sharding: user-based sharding, schema-based sharding, database sharding. So here I just talk about two types, right? The first one is schema-based sharding. What you can do is you can define multiple Galera clusters or MySQL instances, right? And based on which schema you are trying to select, update, insert from, it will write it to the appropriate host group. Okay, this is nice because when you have multiple clusters or MySQL servers, your application just connects to one server, right? Then the other one is database sharding, where you can actually within a single schema push your data to different shards, right? Based on, for us over here in this example, we have something called system ID. So just a bit of context, NinjaVan, we operate in 6 countries. So every single country we operate in has a system ID. So we can push Singapore data to one shard, Malaysian data, Indonesian data to other shards. So it's pretty configurable. But there are some drawbacks, of course. Anything more granular than schema-based sharding will require application level changes. And once you go to sharding, it's honestly very, very hard to go back, right? And once your data gets distributed across nodes, remember you can't do your joins anymore. So all these kind of so-called cross-shard joins need to be shifted to the app layer. Okay. What makes it even more complicated is we talked about the read-write rules just now. Now it needs to be added per shard, right? So per shard, per cluster, that kind of thing. And in general, as engineers, we are lazy because we are smart and we just want to take the simple way out of doing things. So we kind of held back on doing app layer sharding at this point of time. Adding on to that, we also started to experience some issues with Galera. So you know about DB operations. I think there are a lot of DBAs here. We are also quite lazy. So if we have to operate like 100, 200 clusters, it gets very tiring. Of course, you write a lot of operation, a lot of automation to that. But generally, we try to make our lives easier. And so we did that by grouping multiple schemas into Galera clusters to have lesser clusters, right? But what I said just now, right, it doesn't really work well because not write scalable. And the more schemas you put in there, you have higher write traffic, and one day you would have to start to split it. But thankfully with Galera, it's actually quite simple to do that because creating a new node is as easy as just joining the cluster, and then something called a state snapshot transfer will occur, and you get a new node, and you can split it up almost with zero downtime, right? Worst thing is the intra-cluster communication due to the replication uses precious IOPS. And the last thing actually caused quite a number of issues for us. So the way Galera works is that in order for all the nodes to kind of like be up to date with one another, I remember you have the replication. If one of the nodes starts to not be able to catch up, that node will start to publish flow control packets. And basically that results in the whole cluster locking up. Basically the writes are blocked, right? So everyone is allowed to catch up. So this causes a lot of problems on the app layer, of course. Okay, so this one's quite interesting for us as well. So in the early days, actually, we didn't build like the big data engineering. We didn't have the Hadoop, and so we tried to do a very quick solution for BI. And we have smart employees, so everyone knows SQL. And when I mean everyone, even the people inside the warehouse, even the driver supervisors, they know how to write some query to get something. So this was really the quickest way to do some kind of like BI without setting up any proper pipelines. Of course, today we have the pipelines all set up, right? And all we do is we use a front-end tool like Redash, and we query an array of back-end slave databases that we just run the slave channels from the masters. The problem with this is that, when we design the schemas, the indexes there are optimized for our OLTP use cases, right? And a lot of cases when they do analytical styles, you start to have a lot of table scans, again IOPS that slows the entire database down. So and everyone starts relying on it. Everyone knows that this is the place where you can just write queries and get your information. And then because it's slow, everyone is not able to get their information, right? One person can write a crappy table that does a table scan, or a crappy query that does a table scan on, say, 1 terabyte of data, and you're in big trouble, right? So this is what we kind of tried to do to solve that problem. So what we had was we had multiple masters as a source. So you can think of them as individual nodes from multiple Galera clusters. And we ran a multi-channel slave below that layer. So that's our tier 1 operational data store. So basically, we're just merging data from multiple sources into one database, right? And why we merge it is so that they can now do the relational joins across schemas, right? There's actually another solution to that using a federated data source in MySQL, but it's not good because it's an in-memory thing. And if you run an unindexed query on a federated source, you will actually crash the server due to the OOM. And now we have the ODS on the tier 1. We then have this so-called auto-scaling tier 2 slaves, which are just replicas of that tier 1 ODS. So this auto-scaling tier 2 is something that we did some automation to very quickly scale up if we need more read capacity. It's something like you do a snapshot on the disk, and then you bring it up, and that's quite quick. And then you set the replication on the bin log offset, and then you have a new node. So that we can bring up a new node within something like 30 minutes without much operations, just running a simple command, right? And then we have Redash talking to either a ProxySQL or a HA proxy, which load balances the queries, right? Now you see the ghost thing there. I'm not sure if any of you all have utilized this. I'm sure the DBAs know. It's something like the PT online schema change allows us to do the alters, basically the DDLs online without blocking. Because if you understand the MySQL thing, if you do a alter, it does a table copy, it blocks the writes, right? So these tools allow us to do it online. But we actually use Ghost because we wanted to ensure that the slaves don't lag behind too far, right? So what Ghost does is that it actually monitors all the way downstream how much lag you have from the source masters. And if there's too much lag, the the schema change, basically the table copies will slow down, okay? And the problem with this is that if it's lagging too much and new data is being fed into the masters all the time, the Ghost process might actually not even end at all. So basically, you cannot complete the table alter. So that's actually still a problem with us, and we actually solve it by just rebuilding the slaves when the alters finish. So yes, sorry, wrong computer again. Yeah, so one interesting thing we did was we also tried to vertically scale the MySQL storage by using local SSDs instead of the persistence disk, because we get huge amounts of IOPS and throughput when you use local SSDs. The idea is that local SSDs are actually on instant storage in the cloud versus persistent disk, which is communicating through fiber channels in the data center. So you get huge amounts of performance gains. But but you know the problem with that, if you guys have worked with local SSDs, is that in the cloud, when you deploy a VM, you stop the VM and you start again, actually you might not get the same physical machine inside the data center, which means that your data is actually lost the moment you do a reboot, right? So that's quite risky. But for us, it was okay because anyway, if it rebooted, it will just be kicked out of the cluster. We'll create a new one, and then it will just join back the ProxySQL cluster again. Yeah. Okay, so knowing the problems we have, I mean, not just this use case, right? But in terms of our OLTP, our volumes are growing. You have seen how we've grown 6 years from just tens of parcels a day to millions of parcels a day. Our write traffic is going much faster. We're having a lot more schemas. We need an easy way to operate the database, right? So it's time to look for a change, right? What's out there? Should we go NoSQL? Should we go new SQL? What should we do, right? So here are some of the requirements that we look at. I guess one of the important ones for us is that it should be kind of like MySQL compatible because we are lazy. We don't really want to make so much changes to our code. So ideally, it should be as compatible as possible, right? So it should support all the standard SQL grammars. Now, easy operations is as critical to us because if we want to scale up, increase the number of nodes, we want to just declaratively say, okay, we want 10, and then that should happen as much as possible, as easy as possible. We want to be able to do non-blocking DDLs, out of the box if the solution supports it. Read-write scalable, I think that's needless to say. Highly available, we need to be 24/7. CDC, it has to support CDC because CDC is quite core to our use case. We use CDC for data ingestions into our data lake in Parquet. We use CDC to index searchable data in Elasticsearch, and we use CDC for updating our caches as well. So that's critical. The other one is monitoring. We are very, very data driven. We want to know when something's going wrong. And so that we can respond to it, because availability, performance, that's very critical to us, right? And lastly, I said before, we are trying to push everything to Kubernetes. So so we can be lazier. Okay, so what did we explore? A few things: Vitess, CockroachDB, and of course TiDB. Yeah, we have gone through all this, and in the end, we felt that for a solution like Vitess, if you have already been doing application level sharding, that makes a lot of sense, right? Luckily for us, we have not yet. So basically, it gave us a bit more choice. Do we want to go that way and adopt Vitess, or do we want to just be lazy and use something like TiDB? So yeah, please let me hand over the time to Meng Nan, and he will take this to the next step.
Yep. Okay. Thank you, guys. My name is Meng Nan. Okay. I think I will just dive into the topic directly. So after Sean's introduction, I hope you guys are all very thrilled to see like how TiDB really works together with Kubernetes. So let's begin. Okay. So before I jump into the TiDB part, I want to take a little bit time to like introduce what is a control loop in the Kubernetes for the stateless applications. Okay, so basically, if you have an app running in Kubernetes, you mostly will like deal with some of the resources like deployments, config map, and service. Okay, for deployments, it's managing your replicas, and for config map is managing your configuration, and service is to make your application accessible by others. Okay. And let's see if you want to have more replicas for your application to achieve the HA, so the Kubernetes can bring you 2 more pods, let's see. Okay, and of course there is failure recovery. So if one of the application is down, Kubernetes will replace it with a new one. Okay, so all of this magic that Kubernetes is doing is based on something called control loop, which you can also call it reconciliation loop. They are the same thing. Okay, so this loop is an infinite loop that running on the Kubernetes controllers. So what it does is like it's watching the current state and comparing it with the desired state. And if it notices any difference, it will try to make adjustment and try to meet the desired state. Okay, so all of this sounds pretty seamless and it's quite smooth. Okay, but the problem is it's only for the stateless applications. But the question is what makes the stateful application different? And here we got some characteristics that only exist on the stateful applications. Okay, so first one is all the replicas for the stateful apps are different and they have their own state and identity. Okay, it's quite straightforward. It means like if you have a cluster, let's see a cluster of MySQL, and all of the MySQL instances might actually contain different data. So you can't really just replace one with another one. Okay. And the second point is the processes are different for each application. Here I got some examples, let's see, for Elasticsearch or Kafka or even MySQL. So all of these you need to operate and maintain differently. There is no universal procedure for all of these applications. Okay, so it means it could be a heavy burden if you're running a lot of this. Okay. And the last point is about the order matters. Okay, especially for the distributed systems, you need to follow certain sequence when you boot up or like bring down some nodes. You can't just randomly bring up or down any of the members in the cluster. Okay, so based on all of these difficulties we have, so here I introduce the TiDB operators. Okay, so operator pattern is actually similar to what Kubernetes controllers is doing. So here is mainly 2 parts. So firstly, for the operator, you need to deploy the TiDB operator, and it's also running a reconciliation loop as I introduced before. Okay, and the other thing is about the custom resource. For the customer resource, in our scenario, it will be the TiDB cluster. Okay, for the TiDB cluster, once you deploy and you make any changes, the operator will take note of it, and then it will make adjustment accordingly and make your current state meet the desired state. Okay. I think that should be enough talk. So I will show you guys some example here. Okay, so firstly, it's about the scale up. Okay, so let's say if we only have one TiDB node and we want to scale up to 3, all you need to do is change the replica number as I showed just now. And if you go back to this, you will see there is already 3 TiDB nodes running. Okay, and the second example I'm going to show is about backup to GCS. Okay, Okay, so I think we need to wait for a bit for this GIF to replay. Okay, so basically it will start as a YAML file. Okay, you need to prepare the YAML to define the backup. Okay, and then you need to apply this YAML in your Kubernetes. And after you apply this, you should be able to see that the TiDB operator actually pick it up and the status is updating while the backup is ongoing. And after this is completed, you can see it's already on the GCS. Okay. And you can see all those operations are quite easy, quite smooth. And I think I'm proud to say that NinjaVan and TiDB gonna end up marrying and then live happily ever after. And the end of the story, or not. Okay, so sorry, I lied. So the fairy tales don't really exist. So there are still some pitfalls I need to share with you guys. Okay. So first thing is about like be careful when using the local SSD. Sean's already talked about like why we choose local SSD, right? If you take a look of this diagram from a GCP, you can see there is really a huge performance gap between the local SSD and the regional SSD. Okay, so it gives us like the motivation to really try to run our TiDB cluster on the local SSD. Okay, but before you jump into that, I have some tips for you guys. So first one is, please, if you are running your Kubernetes on the cloud, let's see AWS or GCP, please disable your auto repair or auto upgrade. Okay, the reason behind it is just as what Sean said. If when the auto repair or auto upgrade your node, it actually could be replaced by some other machine. So you will just lose your data because your SSD is tied on the machine. Okay. And the second point is about the local volume provisioner. So this thing is what we use to expose the local SSD in the Kubernetes. But as we mentioned before, both of your, so the local SSD is actually a daemon set running on the Kubernetes. So both of these daemon set and your like machine could restart at any time. So you don't want to like accidentally reformat your disk and lose your data. Okay. And the third point is, of course, about the backups and have a standby cluster if possible. So even the worst case happens, you still have a way to recover. Okay. And the second thing is about the MySQL compatibility. So first of all, like I know that TiDB really put like tremendous effort to make it compatible as possible to MySQL. But there's still some small point that could trouble you. Okay, so first one is about the enum elements. Okay, so TiDB doesn't allow you to modify it except you just appending. Okay, so the solution for this is we will just do append only. So we need to avoid like shifting the elements or deleting or updating it. Okay, and actually the second point is in general you should try to avoid use enum type because you try to hide some business logic in the database layer, which might make your application less extendable. Okay. And the second problem you might be facing is changing some column types. Okay, so let's say you change the date to timestamp or vice versa, or you want to change the precision of the decimals. So like all of these, actually, you can't really do it on TiDB. Okay, so you can only recreate the columns instead of altering it. And here comes the second point, and the second is always the best. Okay, so you should establish a schema review workflow. Okay, so we believe with the proper like data schema design and review with your like infrastructure team or with your DBA, it actually should cut like most of the unnecessary column type changes after your schema is already created. Okay, and the next one is about the character set and collation. Okay, so I think most of you should be familiar that MySQL's general collection and the main difference between these two collections is like the MySQL one is actually case insensitive. And like when we first deploy our first cluster, we actually have some problems because like the people who write the query might not really follow the case sensitivity in your database. So you end up have different query result. Okay. But the thing you need to notice that if you want to enable the general collections, you actually have to enable it at the very beginning, at the initialization of your cluster. If you miss that time, you cannot enable it again. Okay, so this is something that actually could like make some troubles, and I believe the team is already working on some solutions for it. Okay. And the last one is about preventing TiDB from OM. Okay, as engineers, I suppose we all hate OMs. Okay, but it's kind of inevitable in a life. So firstly, there is a memory quota per query. Okay, and the second is if the OM really happens, you can choose to cancel the query. Okay, and the third one is you also can use the temporary storage, so it will spill the data to the disk, so it won't really like take too much memory. Okay. But the thing is, even you've done all above it, the OM still could happen. Okay, so the main reason could be the memory quota is actually per query. So if you have a lot of queries and all of them taking a lot of memories, then it means you still could OM. Okay, so the advice is keep an eye on your queries. Okay. So after all the good and the bad, so I want to talk about the future with TiDB. Okay, and so the first challenge is about change of mindset. Okay, so this sounds like a very big topic, but I just want to give you guys one example about it. Okay, so the first is like, do you know, like in TiDB, you should avoid using auto increment primary key if possible. Okay, so this at the first glance is very controversial, I would say, because like if you are familiar with MySQL, you would know like it's really recommended to have an auto increment primary key. Okay, so at first we're gonna take a look like why MySQL in favor of it. Okay, so for you have a diagram here. So this is like an oversimplified version of like how the cluster index looks like in a MySQL DB. Okay, so the cluster index, it just means the data is sitting together with the index. Okay, so and if you see all the leaves, these are called page. So the page is just the basic storage unit in MySQL to store their database files. Okay, and so let's take a look what happens with auto increment primary key. So all you need to do is you have a lot of pages and you just need to appending. Okay, and if there is not enough space, you're gonna have a new page and you keep appending, and it's quite cheap because it's all sequential. Okay, but if you don't have one, and let's say your data will randomly insert into any of the pages, then you will end up have like data movement, and you might have to split your pages, and you might have the memory fragmentation because MySQL will try to read one page at a time to utilize the memory more efficient. If your data is going anywhere, then MySQL need to keep load and offload the pages, so it's really inefficient. Okay, and after that, so we're gonna show you like why TiDB doesn't need that. Okay, so firstly, for the auto increment primary key, so if you do that on TiDB, so mostly all the data will end up to one of the region on one of the TiKV node. Okay, so which means the traffic is pretty much centralized. Okay, but on the right, if you have like let's say a random primary key, and then it actually can distribute the writes to like in your cluster and to different regions, and it will end up a better performance and a higher throughput for sure. Okay, so this is all because of the distributed nature of the TiDB, make it like very different. So the change of mindset is actually quite needed in this. Okay. And the second point is about support our CDC scenarios. Okay, so we mainly have two scenarios. So first is about hard delete. So hard delete is just I want to delete from my database and the data lake. Okay. And for archiving, I just want to delete from my database to release some space. But in the data lake, I still want to keep it. Okay. And the reason, okay, so the approach we do this is we actually rely on the comment in a query. So if you see the example, we do like say delete from orders, and then we have a comment called for archiving. Okay, then like on the consumer side, we will know that we shouldn't delete it from the data lake because it's just for archiving. Okay, and here is our current structure. We have a bunch of MySQL instances, and we use something called Maxwell. So this thing will just as a slave of the MySQL instance, and it will forward the raw query to the Kafka, including other informations. Okay, and then on the other side, the data lake will consume the messages. Okay, and the story is on TiDB, we actually like don't have something like Maxwell, and the problem is it cannot forward the raw query, which means we will lose these comments in the query. And here is the solution that we can think of for now. Okay, so instead of replacing the MySQL at here directly, we actually make the TiDB and the TiCDC. Okay, the TiCDC you can consider is similar as MySQL. Okay, so it will also listen to the TiDB's changes, but this thing cannot forward the raw query. Okay, so the MySQL will still listen to the events and rely on Maxwell to forward the raw query. Okay, so like all the delete action will actually happen on MySQL, so we still can keep this for archiving comments. And okay, here comes the last slides. So of course, we want the minimal downtime migration. Consider we delivering like millions of parcels a day. Okay, so here is how we plan to do it. Okay, so firstly, you have the very basic setup of your application in your Kubernetes, and you have a MySQL which is running on VM. Okay. And the first thing you want to do is, of course, deploy the TiDB. And after you've done that, you need to sync the data to TiDB. Okay, so here, TiDB actually have two tools. So first is DM, stand for data migration. And second is TiDB Lightning. Okay, so if you guys are interested, you can Google it and take a look at the documentation. So, and after the data is in sync with MySQL, and the next step would be cut the connection to MySQL, and then we point to TiDB. Okay, now the TiDB is already serving the application, but we still have one last step, which is using the TiCDC to sync the data back to MySQL. Okay, so this is mostly for like it's served like as a last resort. So let's see if the TiDB has any problems and we have to roll back to MySQL, we still have the fresh data on MySQL. Okay, and I think that's all from me. So I think we probably still have time for Q&A. So we are glad to take any questions if you guys have.